This week we're going to look at two more applications of limits. The first one we're going to do is see how we can use a limit to find this exact area between a curve and the x-axis. And for simplicity, I'm going to refer to that as area under a curve. The second thing we'll do is the application of the limit called the derivative, which we'll actually be studying for about 6-7 weeks starting at the end of this week. But first, let's talk about this area under a curve. So one goal in calculus is to find the following area, this area between a curve and the x-axis. And we could put the area, or we could put the function under the x-axis and go through this same analysis. For now, I'm just going to keep the functions above the x-axis, and then in week maybe like 12 we'll talk about what happens when the function's below the x-axis when we get to section 5.2. So here we have a function. We're going to mark off 2 points on the x-axis. We'll call them A and B, and we want to find the area between the function and the x-axis on that interval A to B. And here we're just going to call it area A. And before finding it exactly, well, to find it exactly, what we're going to do is approximate it. And then we will find that a limit of that approximation will give us the area exactly. So first, let's see how we can approximate it. What we're going to do to approximate it is divide this piece of the x-axis into equal subintervals. So in this example, what did I write? We're going to use 4. But we're going to take this piece of the x-axis, A to B, and divide it into equal subintervals. And then what we're going to do is form rectangles which will approximate strips of this area. They won't be exact, but they will, in the limit, be exact. In which limit? Well, we'll get there. So let's say we want to approximate that area using 4 rectangles. Well, the first thing we notice, well, before we notice anything, let's divide the x-axis into 4 pieces. That's how we're going to approximate them. We're going to first divide the x-axis piece, A to B, into 4 pieces. Let's do that here, and let's do that here. So we'll divide the x-axis into 4 equal pieces. We'll divide the interval A to B on the x-axis into 4 equal pieces. Well, given this subdivision, we could form there are actually several sets of rectangles we could form. We're going to focus on 2 different sets of rectangles we can form. And because we have 2 different sets of rectangles we could form, we're going to define 2 approximations for the area. So how do we form these rectangles? Well, here's what I mean by the rectangles. Because right now on the board I don't see any rectangles. So how are we going to form these rectangles? Well, let's start with this first drawing. Take this place where you divided the x-axis in each spot, go straight up. They should be straight lines. That one's a little off straight. And let's also do that over here. Wow, really bad straight lines there. So here, those aren't rectangles. We can't find the area. We're using rectangles because rectangles' areas are conveniently easy to find. You know, the one side times the other. But these aren't rectangles. If we could find these exact areas, which we eventually will be able to, if we could find these exact areas and add them all up, well, that would give A. But here, we're going to approximate them using rectangles. Which rectangles? Well, what we're going to do with each of these pieces, in this first one, notice we have almost a rectangle here. What we're going to do, we'll look at the base of the rectangle, which is this piece. We'll look at the left endpoint of that piece. We'll go up to the function at that left endpoint, and then we'll use that height to form the first rectangle. So we have a piece of the x-axis. Here we're going to look at the left side of that base of the rectangle, go up to the function, go over, and now we have a rectangle. And we're going to do that with all of these pieces. So for the next one, here's the base. Look at the left side of that base. Go up here. That point up there will define the height of the rectangle. And we're going to do that for these other 2 pieces. Here's the base piece. Look at the left side of that base. Go up to the function. use that to form the other side of the rectangle. And then for this last piece, we'll do the same thing. We're going to take this the base portion of the rectangle, look at the left side of it, use that to define the height of the rectangle, and go over. And right here, an approximation of this area that we will use is given by the area of this rectangle plus the area of that rectangle plus the area of that rectangle plus the area of that rectangle. And notice here that if we add in this first one the areas of these four rectangles together, it's not going to give us A exactly, because we have these wedge, triangular wedge type pieces which are not included. There are these four things here which are preventing our approximation from being exact. But we're going to use that approximation, and we'll see that we can eventually use that to make the area exact. So that's one set of the rectangles we could choose. The other set we're going to form essentially the same way, but when looking at the base, notice or remember here we used the left side of the base to define the height. Instead of using the left side of the base, we're going to use the right side of the base to define the height. So we'll use this point, we'll go up here, and we'll go in that direction. We'll go toward that direction to form the height of the first rectangle. So the first rectangle over here, we used the left endpoint to define the height. For the first rectangle over here, we're using the right endpoint to define the height. And this will give us some area. And we can find areas of rectangles. Rectangles are convenient. And we're going to do that for all four of these pieces. So for the next piece of the base, we have that piece of the base, take the right endpoint, use that to define the height of the next rectangle. And again, we're going in that direction, because this bottom thing is going to be the base of the rectangle, and we use the right endpoint. So to form the other side, you'd have to go that way if you trace it up to that. That will be our next rectangle, and then we want to do that with these other two pieces as well. So we have that base of the rectangle, the right endpoint, go up here. That'll make a rectangle. And then do that with the last one. We have the base. Here's the right endpoint on the base. So we'll go up here to define the height of the rectangle, and we'll fill in that rectangle like that. So these two sets of rectangles are the sets of rectangles we will use. The one we used forming the left endpoints and the one we used forming the right endpoints. And we have two different sets of rectangles. We're going to define two different approximations based on those diagrams. I'm just going to look at my notes to make sure I phrase it exactly the way I want. Let's use a black marker. So for this reason, we define two approximations of the area. I'm going to write the two definitions under the appropriate diagrams. L, capital L, since we use the left endpoints. And here I'm going to call it L4, because there are four rectangles. L4 is the combined area of the rectangles found using left endpoints. So L4 is going to be the area of those four rectangles added together. And similarly, R4, for right endpoint, R4 is the combined area of the rectangles found using right endpoints. When I define things, I usually underline the definition. If you wanted to underline something here, it would be L4 and N4, or L4 and R4. So right here we have two different approximations, and in a moment we're going to do some computations finding these approximations. But how can we use this to find the exact area? Our goal a goal in calculus is to find the exact area. Our goal here is to find the exact area. Well, how can we do that? Notice in both of these are approximations. This approximation over here is a little under A because of these wedges that aren't included. Over here, if you add all these areas, you're going to get something that's larger than A because of these wedge-like things that are included in our approximation. So neither of these gives the area exactly. But how can we use this to find the exact area? Well, what would happen? Say you divided this interval up even more. Well, you can imagine if you divided this interval up more, these wedges, while there would be more of them, get smaller. And similarly over here, if you divide it into more rectangles, say 100 rectangles, and there's a diagram in section 5.1, I believe, of the book that shows this. If you divide that into more rectangles, divide the x-axis more, these error terms are going to get smaller. So here, if we let n equal the number of rectangles, so there we have 4 rectangles, there we also have 4 rectangles, but here, I'll put this as a remark, this should be a little separate from the rest of those comments. So after these definitions we make a remark. If we let n equal the number of rectangles that we form, so n is how much we're chopping up this x-axis, if we let n be the number of rectangles, well then our approximations would be Ln and Rn, L sub n, R sub n. But a major result in math is the following theorem. I did just write it in notation. Okay. Then we have this theorem. Limit n goes to infinity of Ln equals, I'll write it like this. So theorem limit n goes to infinity of Ln equals A equals the limit as n goes to infinity of Rn. So what is happening here? We're letting n be the number of rectangles. And then, without the limits, we have an approximation of the area using that number of rectangles. But this theorem says if we let that number of rectangles go to infinity, which we can do, we have limits to infinity, we're going to let that number of rectangles go to infinity. And this theorem says if we let the number of rectangles go to infinity, this approximation becomes exact, meaning this combined error term will go to 0 as we do more and more rectangles. Similarly, if we let the number of rectangles go to infinity, this approximation will approach A, meaning this approximation will become exact. This approximation will give the exact area in the limit. This is a very important result in math. So next, before we talk more about this result, this is kind of a foreshadowing, you could say. But before we talk about this and more, we're going to more formally define these approximations in a moment. But before we get there, let's just look at a couple computations of this approximation. Example. Approximate the area under the curve, or again, area under the curve means the area between the curve and the x-axis. In this case, on the interval 1 to 3, using 2 rectangles, 4 rectangles, 8 rectangles, 3 rectangles, 4 8 rectangles. We're just going to set it up. We're not going to actually find the number. We'll see why in a moment. Function x squared plus 3. Approximate the area using these rectangles. So for the first one, 2 rectangles, well, what would that look like? Well, let's draw this function. We can draw this function. X squared plus 3 looks something like that. X squared plus 3. What interval? 1 to 3? Well, let's mark off 1 to 3. There's 1. There's 3. And we want to, for part A, use 2 rectangles. So we want to divide this interval into 2 pieces. Now, we're going to need this x value between them. What is that x value? Well, it's the point immediately between 1 and 3. So in this case, that's 2. In doing these, I usually find that finding the x values is actually the most difficult part of these. Because after that, we'll see in these computations, after that, we're just adding areas of rectangles once we find the appropriate x value. So we've seen 2 different approximations. For this example, I'll show you both approximations in each part. But you know, if you're asked to approximate something on a test or a quiz, well, I guess we don't do quizzes, on a test or a homework, you can use only one of the approximations if you want. So I will do both. You can do only one if you want. So first, let's do the left-hand approximation. Now, how do we form the rectangles using the left endpoints? Well, here's a base. We look at the left endpoint and we form the height like that. The next one, there's the base. We look at the left endpoint. We form the height like that. So we have 2 rectangles. We need to find their areas and add them together. Now, when we were setting this up, we wanted these bases of the rectangles to all be the same. The reason we do that is so the algebra works out more nicely than it could if you don't. I mean, you could, if you want, do a similar definition, set up a similar limit where the bases aren't the same, but that's not advised. We will just use these 2 approximations where we make the base the same. If you didn't, you'd probably have to define a bunch of extra variables. So let's not do that. Let's make the base the same in each case. So here, what is the length of this? Well, it's the area of the first triangle, the rectangle. This side times this side. What is this side? Well, 2 minus 1. 1. What is this side? What is that side? Well, it's a y value. It's a piece of the y-axis. Which y value is it? It's the y value when x equals 1. What y value occurs when x equals 1? Well, x equals 1 up here. 1 squared plus 3 is 4. So how will I write this? I'll do 1. I guess I'll use a parentheses for this one. 1 times 4 is the area of the first rectangle. 1, because that's this base. 4 is that height because f of 1 equals 4. Plus, we need the second rectangle. The second rectangle's area is this side times that side. This side, again, is 1. It's 3 minus 2. We set it up to be the same as that one. What is the other side of this rectangle? Well, it's this y value. It is the y value which occurs when x equals 2. Which y value occurs when x equals 2? 2 squared plus 3 is 7. So L4 is 11. And notice with this function, this does give an under approximation of the actual area. But for our approximation, 2 rectangles, the area rectangle is the one side times the other. The one side in this case is 1. The other side is given by the function evaluated at 1 and the function evaluated at 2. How about the other approximation? So if you had this question, part A, on a homework or something, and you just wrote L2 like that, that would get full credit. How about the right-hand approximation? Well, I'm going to draw this function again for this one. And again, we have the interval 1 to 3. We're dividing it into 2 pieces. So the point immediately between 1 and 3 is 2. This function is what? X squared plus 3. And we need the rectangles formed by using right endpoint. So the base of this is that. We use the right endpoint to define the height of the rectangle, and we get that rectangle. Here, there's the base, use the right endpoint, go up here, and form a rectangle. So again, we have two rectangles, this time formed using the right endpoints, and now we need to do the area of the one plus the area of the other. Base of the first rectangle, again, is 1. The height of the first rectangle, well, the height is this y value. That is the function evaluated at x equals 2, which here we get 2 squared plus 3, which is 7. So we have 1 times 7 for that first rectangle. Next, we have the base, again, is 1. And what's the height? Well, the height now is given by this y value. The function evaluated at 3. The function evaluated at 3, 9 plus 3 is 12. So here we get 7 plus 12, which is 19 for that other approximation. So both approximations, we used our diagram to form the rectangles, and then really to find the areas, I just looked at the diagrams and noticed, well, these y values are given by the function, these y values given by the function. Notice that right-hand approximation gives an over-approximation based on our diagram. We could observe right here that the exact area between this curve and the x-axis is between between 11 and 19. We will see by the end of the video, or maybe a separate video, but we will see that the area is 14 2/3. So next, let's do part B using 4 rectangles. And again, for this one, I'm going to draw a diagram, but I am going to set up the equations a little differently. Because in that first example, it may not have been obvious why it's convenient to make the bases all the same. In this one, we will see why. So where am I going to do this? Let's do it here. No, it's too far over. Let's do it here. So again, we have this function. Again, we're going to divide it, or we're going to take the interval 1 to 3. I'm going to move 1 over a little more. So here we'll say 1 is there, 3 is there. This function is x squared plus 3. But now, first we're going to do the left approximation. Now we're going to divide this interval into 4 pieces. Well, how do we divide it into 4 pieces? Well, we can do it like this. Divide it in half, and then divide each half in half. 2 squared is 4. Well, now we need to label these x values. Well, the one where we divided it in half is 2, because 2 is right between 1 and 3. What is the point immediately between 1 and 2? 1 and a half, also known as 3 halves. What's the point immediately between 2 and 3? 2 and a half, also known as 5 halves. So we have those x values. And now we can form our rectangles and add areas together. Before we do that, let's talk a little more about how to find these x values. So here, just from the diagram and dividing it in half, I just said, well, the one immediately between is 2, the one immediately between those others is 1.5. But how could we find those algebraically? Well, let's say, I'm going to write this, then I'm going to erase it. To find x-axis points. Well, how would we find the x-axis points? This will become quite useful, especially in part D, which is why I actually have 3 out of order. To find the x-axis points, what would we do? Well, we can do it algebraically. What we're actually doing is dividing this interval 1 to 3 into 4 pieces. So we'll take our interval, 1 to 3. It has length 3 minus 1, shoot. And we're dividing it into 4 pieces. So that tells us that this quantity is going to be the width of each of these rectangles. So what is this, 2/4? So it's 1/2. Well, okay, there's observation 1, that we took the interval 1 to 3 and divided it into 4 pieces. which gave us a length of 1/2 for each of the bases of the rectangle. Well, how can we use that? Well, we know the length of each base of each rectangle is 1/2. If we're starting at 1 and this length is 1/2, then the next x value is 1 plus 1/2. 3/2. So I'll say 1 plus 1/2. And what would the next one be? Well, the next one would be 3/2 plus another 1/2. 3/2 plus 1/2, 4/2, which is 2. And how would you find the next one? Well, it's 1/2 from 2. So I'll say 3. This might not fit nicely. Maybe I'll put a square around it. Yeah, okay, that looks sort of fine. So we went from 3/2 over 1/2 to get 2. The next one, we start at 2, we go over 1/2, and we get 2 1/2, which is 5/2. So that's 2 plus this length, 1/2. And then the last one, 5/2 plus 1/2, 6/2, which is 3. So you could find them using your diagram. Well, I mean, there are some examples where 3 is easier if I took the interval 1 to 4. But you could do it algebraically. You could do it just from labeling your points and dividing them as is appropriate. So we'll see a little more of that algebra in part D. And also, you know, I find finding these x values the most difficult part of this, because once they're found, we just have to do rectangles. But what's convenient about, another thing that's convenient about it, is we can check our work by making that observation that each piece is length 1/2, and then just counting. So here, 1 is how many halves? 1 is 2/2. So we have 2/2, 3/2, 4/2, 5/2, 6/2. And these are going to count out in a similar arithmetic way. 2/2, 3/2, 4/2, 5/2, 6/2. So whichever way you want to find your x values is okay with me, so long as they are reduced fractions. But here, we want to approximate the area using 4 rectangles. So first, let's find L4. I'm going to write it on the next board, I think. So here, L4. Well, let's form our rectangles. Use the left endpoint, left endpoint, left endpoint, left endpoint. And in this case, it would look like that. And we'd have these areas. Well, what is the length of the base of this first rectangle? Well, 3/2 minus 1 is 1/2. So the first one, I'm going to move it over a little. You'll notice I have 2 erasers here. This is a magic eraser. It works pretty well on these, but since they are, you know, they function as sandpaper does, I do get a little nervous using them on these boards, but they don't seem to have hurt it. It works much better than the standard whiteboard eraser, especially when these get, you know, all dirty. Where were we? L4, the base is 1/2. What's the height? Well, the height is given by the function evaluated at 1. What is that? Well, it's 4. I'm just going to write it, in this case, as f of 1, and then we'll find all these numbers. Is this going to fit on that board? It should. So the first one is 1/2 times that height, which is f of 1. What's the next one? Well, again, it's 1/2 times this height, f at 3/2. So plus 1/2 times f, in this case, at 3/2. What's the next one? Well, again, it's 1/2. It's set up to always be 1/2 in this case, times this height, f at 2. And what's the fourth rectangle? Well, it's this base, which is 1/2 again, times this height, which is f at 5/2. So we have plus 1/2 times f at 5/2. So this is going to give us our approximation if we just simplify all these numbers. But before doing any simplification, let's make a convenient algebraic observation. One of the reasons we divide the x-axis into equal pieces is so that in this step we can factor out that factor, which is a half. Take a half out of each piece. Take a half out of each piece and you're left with a half times that quantity. And this right here is the general form these approximations are going to take as we do them. So in doing these, you can jump straight to something like this, which we will do in Part C. So we have this. We just have to find this function, evaluate all those points, add a bunch of numbers together. So let's do that. A half, f of 1, don't forget the multiply. F of 1 is 4. F of 3 halves. 3 halves squared is 9 fourths. 9 fourths plus 3, 9 fourths plus 12 fourths, 21 fourths. I won't erase that yet. F of 2 is 2 squared plus 3, 7. F of 5 halves squared plus 3, 25 fourths plus 3. Turn the heat down. Turn it down to 49. F of 5 halves is 25 fourths plus 3. 3 is 12 fourths, 25 fourths plus 12 fourths is 37 fourths. So we have to add these numbers together. Now you could do that denominator thing and add things. I'm not going to do that. I'm not going to do it yet. Because we can combine the things we can combine. 7 and 4 make 11. 21 and 37 make what? 58. So we have 58 fourths, which reduces to 29 halves. So we added these whole numbers and then added the fourths. So we got 11 plus 29 halves. What's 11 plus 29 halves? Oh, I don't know. 22 halves plus 29 halves? 22 plus 29 is 51. And a half of 51 halves, it's not 51 halves, is 51 fourths. So once you have all these x values labeled, there is some tedious simplification, which could be made much more tedious. But it's just adding the numbers in whichever way you feel most comfortable. I like, at a step like this, adding the whole numbers together and adding the fourths together and separating them. It helps keep me organized. Plus, I don't really like combining fractions that much, so I try to avoid it as much as possible. So there we have our left approximation. Let's next do the right-hand approximation. And to do that, I'm just going to redraw this. Three, 1, again we're dividing into 4 pieces, we're going to get the same values. 2 halves, 3 halves, 4 halves, 5 halves, 6 halves. 5 halves is not 5 fifths. But now we're going to use the right-hand endpoints. So we're going to form our rectangles going like this. And these are going to, we're going to have to find those areas. Now, to do this, I'm going to erase these last 2 boards of work. You'll see why in a moment. So let's find R4. R4, well, the first rectangle base is a half. Actually, right now, all of these bases are going to be a half, so let's just pull out that half. So the first one has base a half. The height is given by, in this case, the function evaluated at 3 halves. That height forms our rectangle. The next one, length a half on the base times the function evaluated at 2. So there's the 1/2 times the function evaluated at 2. The next rectangle, again 1/2 times the function evaluated at 5/2. And the last one, again 1/2 times the function evaluated at 3. So now we have to find these numbers and simplify, add them together, and distribute the half. But before we do that, let's just compare this second line to this third line. What are the real differences in these two approximations? Well, this thing shows up in both, this thing shows up in both, this thing shows up in both. This one shows up in the left one, this one shows up in the right one. I usually include this diagram later in my discussion of this. I'm going to throw it right here on the board now. In your notes, if you're taking notes, you might want to leave a gap for the rest of this computation. Or you can just find it, pause the video now, find it now. It'll turn into 67/4. I didn't just do that in my head. I've done this example a bunch of times. But no, I'm going to include it after doing it. No, I'll include it now. I already said I'd include it now, so let's include it now. What are we actually doing with this? Well, first, let's observe, in forming these rectangles, we don't actually need to draw out the function. What really matters, I'm going to write this as an observation. So this observation should go after the rest of that computation. Observe. What should we observe? Well, let's take 1 to 3. So there's 1, there's 3, there's 2, there's 3/2, there's 5/2. Observe. Which of these endpoints are we using in our computation of the left-hand approximation? 1, 3/2, 2, 5/2. The left-hand endpoints. 1, 3/2, 2, and 5/2 are used in the left-hand approximation. So let's write that. Observe. Filled in circle are used in L4, let's just say for simplicity. Which ones are used in the right-hand approximation? Well, 3/2, 2, 5/2, 3. 3/2, 2, 5/2, 3. The right-hand endpoints. Let's put large circles around them. So the ones filled in are used in L4. The ones with large circle are used in R4. And the ones with both are used in both. Now that's a convenient observation. When we do part C, I'm going to make an observation like this because I'm not going to actually draw out the function. I'm just going to use a number line like that. So let's find this number. Well, half f of 3/2. What's f of 3/2? We already found that. It was, I forget, 21/4. F of 2 was 7. F of 5/2 was 37/4. F of 3, I mean, we actually found that in part A. I don't remember. F of 3 is 12. Now we have to add these numbers together. A half, 7 plus 12 is 19. 21/4 plus 37/4 is again 58/4, which reduces to 29/2. And now we need a half of what? 19 plus 29/2. 19 is 38/2. 38 plus 30 is 68. So we have a half of 67/2. Which is 67/4. So again, I guess I could ask you to find both approximations. I think on the worksheet I do say find both approximations because it's a worksheet. But if I don't say find both approximations, then either this answer up here simplified to 51/4 or this answer down here simplified to 67/4 would work. So let's next do part C. And part C says just set up. Just set up means get it to like one of those two lines. Well, get it to each of those two lines if you need to do both. So let's do part C with 8 rectangles, see what we get. These approximations have a lot of writing in them. Actually, I'm going to erase that observation. I was thinking of leaving it up. I'm going to erase this for part C. So using 8 rectangles. Well, I'm not even going to draw the function. I'm just going to draw our number line and use that observation. We have 1 to 3. We're dividing it into 8 pieces. 8 is 2 cubed, which is nice. So half is 2. Half is 3 halves. Half again. What is between 4/4 and 6/4? Well, 5/4. What is between 6/4 and 2? 7/4. What is between 2 and 3? 2 1/2. What is between 8/4 and 10/4? 9/4. What is between 10/4 and 12/4? 11/4. So we're dividing it into 8 pieces, and we get those x values. If you didn't do it in that dividing in half and halfway, how would you do it? How would you get these? Well, so I'll say alternately, then I'll erase this after I write it. Alternatively, not alternately, you would do again the interval 3 minus 1. In this case, we're dividing it into 8 pieces. 2 divided by 8 is 1/4. And then you would go 1. You'd go 1, and then the next one over is 1 and 1/4. 5/4. Then the next one is 5/4 and 1/4. 6/4. The next one is 6/4 and 1/4. 7/4, and so on. So either way you want to do that is fine with me. Actually, I could have left this on. I'll leave it. So 1 plus 1/4 is 5/4. The next one is 6/4, and so on. So I'm going to do these approximations over here. And again, to check ourselves, we could count through these. Count by quarters. 4/4, 5/4, 6/4, 7/4, 8/4, 9/4, 10/4, 11/4, 12/4. Now, how do we do our approximation? Always keep in mind with these approximations, especially if you do the shortcut that I'm doing here. When you draw out the function and draw the rectangles, well, when I draw out the function and draw out the rectangles, I find myself much less likely to make an error in doing these. But if I do the shortcut, I always keep in mind we're adding areas of rectangles. Base times height. The one side times the other side. What is the one side here? Well, we wrote it here. It's 1/4. Or you can look at this. 5/4 minus 1 is 1/4. The one side is 1/4. And how about the other sides? Well, for the left-hand approximation, we're going to use all of the left endpoints. Don't use the last one because we're not using the we're using only the left endpoints. So we have 1/4, and then the function evaluated each of those added together. So f of 1 plus f of 5/4 plus f of 6/4 plus f of 7/4. All these reduced, of course. Plus f of 2 8/4 plus f of 9/4 plus f of 10/4 5 halves plus f of 11/4. Now my instinct was to start writing it down here, which is why I wanted to erase it. I always underestimate how large my writing is, especially on these boards. So we did the one side times the sum of the function evaluated all the others. And if you distribute this out, you'll see there are 8 rectangles, a quarter times f of 1, a quarter times f of 5 quarters, and so on. So here, the one side is a quarter, and the other side is the function evaluated at each of these. And if you want, you could draw out the function and draw out the rectangles. I definitely find that doing that helps solidify in your mind that you're thinking of areas of rectangles. So before, when I mentioned doing the shortcut, I sometimes forget that. There have been times in my life where I would forget to write this one side. And it'd be wrong if I just wrote that. But if you keep in mind areas of rectangles, that's a way to avoid that pitfall. So there was the left-hand approximation. Let's try to fit the right one on one line. Might not. But how do we do the right-hand approximation? Well, we use the right endpoints. Notice the only real difference is including the first one and the last one. To do the right-hand approximation, again, we have areas of rectangles. The one side is a quarter from that. The other side, well, the other sides are given by f of 5 quarters, f of 6 quarters, and so on. So f of 5 quarters plus f of 6 quarters plus f of 7 quarters plus f of 8 quarters plus f of 9 quarters plus f of 10 quarters plus f of 11 quarters, and I didn't fit it on this board, plus f of the last one, f of 12 quarters. I guess you can write it like that. And when I say set up as I wrote here, you can just stop there. And adding these numbers together, not worth doing with this many. With 4 of them, or 3 of them, or 2 of them, it is worth doing, just to keep your number skills sharp. But with these, that's just going to be annoying. So we have these 2 approximations. And notice, let's use the other colored marker. Notice those blue underlined terms do show up in both of these. Because they're circled and dotted. And f of 1 shows up in only one, f of 3 shows up in only the other one. So next we have part D. Use 3 rectangles. And why did I include this one last? Well, because of the interval we're using and because of the number of rectangles. So let's first break the interval 1 to 3 down into 3 pieces. D. 3 rectangles. Yeah, I'll draw the function. Why not? Well, why not? Because it's not completely necessary. But I'll draw the function anyway. Try finding these x values. So try pausing this and finding the x values before I find them. See how it goes. Well, that's what they are. 5/3, 7/3. Where do they come from? Well, how do we find them? To find them when we have an interval like this and a number of rectangles like that, I do like to go to the length of the interval divided into how many rectangles, how many pieces type argument. So to find 5/3, how did we do that? Well, we still have the interval 1 to 3, so that has length 3 minus 1. We're still dividing it into 3 pieces. And what does that equal? Well, it equals 2/3, which actually tells us that the base for each of our rectangles is going to be 2/3. But how do we find the x value from there? Well, that's each length is 2/3, so we start at 1 and we add 2/3. So 1 plus 2/3. thirds. That's a terrible 3. And then the next one is a 1 plus 2 thirds. 3 thirds plus 2 thirds is 5 thirds. The next one, 5 thirds plus 2 thirds, 7 thirds. And then 7 thirds plus 2 thirds gives us 3 9 thirds. Erase that. And before doing our approximations, let us check our x values by counting these out. 3 thirds, 5 thirds, 7 thirds, 9 thirds. That does follow our pattern. In the other ones, it counted 1, 2, 3, 4, 5, 6, 7, 8, or I guess it didn't start at 1. They didn't skip numbers in the numerators, but here, notice it does go 3 to 5 to 7 to 9 in the numerators. So it is still an arithmetic sequence. So 3 thirds, 5 thirds, 7 thirds, 9 thirds. And how are we going to do our approximation? Well, we have our rectangles. The base of each rectangle, in this case, is 2 thirds. For the left approximation, we use f at 1. Then we use f at 5 thirds. Then we use f at 7 thirds. And now we have to add these numbers. These numbers are going to work out a little less conveniently than the previous ones. F of 1, where's our function? I probably should have written it here, is 4. F of 5 thirds. What's f of 5 thirds? 25 ninths plus 3. 25 ninths plus 3. 3 is how many ninths? 27 ninths. 25 plus 27 is 52. So we have 52 ninths. F of 7 thirds, 49 ninths plus 3. What's 3? 3 is 27 ninths. 49 plus 27 is 50 plus 26. You know, if you do that addition, like writing things down, I mean, I certainly would recommend against if you were writing the addition down. There are faster ways of doing it than... What am I doing? There are faster ways of doing it than saying it's like this, if you write it down. But in my head, I find it easiest to, you know, get one of the numbers to 0. Either way. And when you add a lot of numbers, you start noticing some shortcuts. So we have all these numbers we have to add together. So let's do that. So this equals what? 2 thirds times 4 plus, what is that, 128 ninths? That's a large number, sort of. And then you step back, make sure you added it right. Then what? 2 thirds, 4 plus 128 ninths. 4 is 36 ninths. 36 plus 128 is 164 ninths. Then we multiply these. 2 and 164 is 328. 9 and 3 is 27. And that doesn't reduce because that has no 3's in it. So we have our left-hand approximation. So now let's do our right-hand approximation. I guess I didn't have to erase that. I have to erase this. Now let's do our right-hand approximation, which would use these rectangles. I'm going to do it over here. So what is our right-hand approximation going to be? Well, it's R3. The base is 2 thirds in each case. The heights are given by... What are the heights given by? F of 5 thirds plus F of 7 thirds plus F at 3. So what does this equal? Well, F of 5 thirds is 52 ninths, F of 7 thirds is 76 ninths, F of 3 is 12. And now we have to add these together. So again, we get 2 thirds, that's what, 128 ninths? And the 12 I just moved out front because I like it out front. 12, do we know our 12 times tables? Well, yes, of course we do. Do we know our 13 times tables? Not necessarily. But the 12s are convenient to know. 12 and 9 is 108. 120 minus 12, 108. So 108 plus 128 is 236. Now the only 13 times tables that I ever actually see, 13 squared, 169. 13 times 7 is 91, which is convenient to keep in mind so that you can conclude 91 is not prime, if you were so inclined. Then you step back, make sure you added correctly. Yes. And then 2 times 236, 472. 3 and 9 is 27, and that doesn't reduce. That has no 3's. So here we found our other approximations. Now, on a test or a homework, odds are quite high that I wouldn't, they wouldn't turn into. Odds are the numbers they would turn into would look more like the numbers in part B than part D. But, these approximations, they could get complicated in their simplification. But the setting up of these approximations does not get necessarily more complicated than something like one with 8 rectangles. To do that, I always like to draw out a number line. And then I always like to find these x values. And then I always like to keep in mind that we are doing areas of rectangles. Because when you think only about areas of rectangles, we've known area of a rectangle for a long time. It's the one side times the other. You've seen that for many years. So I personally think that starting the thought on these with areas of rectangles is a more convenient way of looking at it than looking at that formula. Because keeping areas of rectangles in mind allows us to get to that formula just from using one side times the other. I guess I'll erase this. So we have this computation. Notice in all of these, because of the functions we chose, well, because of the function I chose, in all cases, the left-hand approximation gave an under approximation and the right-hand approximation gave an over approximation. That's not necessarily always the case. So I'm just going to write that down as a remark. Remark. Given this function, for f of x as defined in this remark, okay, I'll do it like this. For this function, let's say equals 1 over x. We know what that function, we know what a function like this looks like. For f of x equals 1 over x on, say, 1 to 3, that's the interval we've been looking at, what would that approximation look like? Well, the function would look like that, and we would have our division of 1 to 3 like this. But for this function, ln gives an over approximation, and Rn gives an under approximation. So in that example, in this example, and in the first diagram we did, the left-hand approximation always gave an under approximation. The right-hand approximation always gave an over approximation. But that's not necessarily the case all the time for the left and right-hand point, or left and right-hand approximations. As you can see from this example, f of x is 1 over x. Well, in this one we have ln gives an over approximation, Rn gives an under approximation. Well, why is that? Well, the left endpoints would give us rectangles like that. The right-hand endpoints on 1 to 3 would give us rectangles like this. Maybe I'll shade them in. Maybe I should have drawn that a little bigger. That's okay. So the left-hand approximation doesn't always give an under-approximation, and the right-hand approximation doesn't always give an over-approximation, and it does depend on whether the function's going up or going down. So, on one of my tests last year, there were a couple answers that said this is an under-approximation because it's left-hand. And that's not necessarily the case. That depends on the function. A function like this one gave us an under-approximation for the left hand. A function like this one would give us an over-approximation. So, if you have to figure out whether it's an over-approximation or an under-approximation, one way to do that is to draw the function and draw out the rectangles you are considering. So we've done a few approximations and seen those computations. Let's formalize these approximations a little more. And in formalizing these definitions, we will be able to see how we can then find the exact area using a limit. So we now will find the exact area, and we'll start with this definition. Let f be defined on a to b, closed. Divide a to b into n sub-intervals of equal width delta x. We're taking this interval, dividing it up into n pieces, and those n pieces we're going to use to form our rectangles. And we're going to call these sub-intervals x0, x1, x1, x2, all the way up to xn minus 1, xn. And I'm going to put a diagram over here in your notes if you take notes. This diagram, well, number line I'm going to put up here, I would put under this number 2. So call them these subintervals. Well, where does that come from? Well, what do we have? Well, we have the interval a to b, and we're dividing this up into n pieces, and we can't actually, draw out n pieces. I mean, that doesn't make sense. N is variable. But here's what we're doing. We're dividing it up. We're going to call the first one inside here x1, then x2, x3, x4, x5, until we get to the second last one we'll call x sub n minus 1. And we're just going to redefine the first one as, well, maybe I'll say it like this. We'll redefine the first one as x sub 0. So a equals x sub 0, and b equals x sub n. Those are vertical equal signs. So we're breaking up our interval into n pieces, and we're labeling the x values. So the first one, we're not going to call it a, b anymore. It'll be helpful to keep that in mind. But the first one we'll call x0, the next one x1, x2, x3, all the way up until, let's just get rid of those, I don't need those, all the way up until we get to the second last one, xn minus 1, and then the last one we're going to call xn. So we're counting out these x values starting at 0 and ending at n, and we're using the subscript to count them out. But in doing this, notice what each subinterval is. Each subinterval is now x0 to x1, x1 to x2, x2 to x3, up until we get to xn minus 1 to xn. So we're dividing the interval into n subintervals of equal width delta x. Each of these will have width delta x. Call these subintervals x0 to x1, x1 to x2, and so on, up to xn minus 1 to xn. And now with that notation, we can define our approximations more formally. Then, number 1, L sub n equals the sum, capital sigma, the Greek letter sigma for our sum notation. The sum from I equals 1 to n of x sub, the sum from I equals 1 to n of f of x sub I minus 1 times delta x. So here we have the sum. We're adding together for these, remember, we're adding n rectangles. So the sum is going to go from 1 to n. That tells us we're adding n things together. And then we have f sub x, I should say it correctly, f of x sub I minus 1 times delta x. That gives the left endpoint approximation, sometimes called a left Riemann sum, or sometimes called a Riemann sum using left endpoints. Riemann, R-I-E-M-A-N-N, is named after the mathematician Riemann from the early 1800s. He did a lot of work in many branches of math, kind of related to this, but he also formalized a lot of our understanding of limits. Well, he was one of several mathematicians who helped develop the concept of a limit. And he did these approximations as well and formalized them. So we could call it a left Riemann sum using left endpoints. Either way, same definition. And similarly, Rn, the sum from I equals 1 to n of f of x sub I delta x is the right endpoint approximation, a right Riemann sum. Now let's talk a little bit about these formulas. I see these formulas, both of these, as adding areas of lots of rectangles, of n rectangles in each case. Why is that? Well, ignore the sum for now. The sum, well, let's not ignore the sum for now. The sum just says we're adding n things together. Which n things are we adding? Well, we know we are going to be adding rectangles, but why are these rectangles? Well, there are two pieces. F of x sub I minus 1, delta x. The only difference in these definitions with our notation is the subscript on x. For this one, it's x sub I minus 1. For this one, it's x sub I. But in both of them, we're adding n things together, and we have two things multiplied. Well, if we're adding areas of rectangles, these two things must give us the areas of rectangles. Now, why do they give us the area of rectangles? Well, area of rectangle, one side times the other. The one side is the base, which is always delta x. So we have a delta x. You could do a similar definition by taking this delta x outside of the sum. I'm not going to do it. I'm just going to write it like this. So here we have one side of the rectangle. What's the other side of the rectangle? Well, the other side of the rectangle, remember, is given by the function evaluated at those points. So here we have, in both cases, function evaluated at something times the base of a rectangle. So we have rectangles that we're adding together. Now, why do these give the right ones? Well, to figure out why they give the right ones, well, the correct ones, I should say, we look at our notation. There are a couple different notations, well, a couple different ways you could set up the notation. I used this one because the book used it. But these underscript and overscript on the sum notation tell us how we're going to be counting through these rectangles. And they tell us we're going to start at I equals 1 and go up to n. Well, what happens when I equals 1 here? F of x sub I minus 1. I equals 1 would tell us f of x sub 0. Well, that tells us the first one looks at x sub 0. What about I equals 2? The next one would be I equals 2. When I equals 2, what do you get? F of x sub 2 minus 1. F of x sub 1. And so on until you get to the last number, n. What happens when you let I equal n? Well, you get f of x sub n minus 1, which is this second last one. So with all of those, we are getting the correct endpoints for our left-hand approximation. And now for the right ones, why do they give the right ones? Well, why does this give the correct ones? Well, if I equals 1, the first one occurs when I equals 1, you get f of x sub 1. The next one, when I equals 2, you get f of x sub 2. And so on until the last one, let I equal n, you get f of x sub n. Second last one would be n minus 1. So they do follow the same type of diagram we saw before. in breaking down these x values into right and left endpoints. Now we have this notation. Our goal is to find the exact area. So let's say then, so if you're taking notes, this would follow under this, and then after that you could say then we have this theorem. Well, n equals the number of rectangles. I mean, there are actually no rectangles written in this formal definition. The number of subintervals will form the number of rectangles, but theorem, limit as n goes to infinity of ln equals the limit, well, I should write it the way I wrote it before. So at the beginning of the video I said equals a, the area we want, equals the limit as n goes to infinity of Rn. So they're equal. If we need to find the exact area, we don't have to do the limit of this first one and the limit of the second one. We could just do one of the limits. So let's find the exact area. Let's find the exact area, and for finding the exact area, I'm going to use this second one. I'm going to use the right-hand approximation, just because of the subscript being I in that definition. So I'm going to erase everything but that. And let's do a computation. Now, in the middle of this computation, we are going to have to make note of a couple results that we'll use for it, but we'll see. So, example. Find the exact area between f of x equals x squared plus 3 and, well, I don't know, maybe I guess I've been saying area under the curve, so let's say area under the curve here. Find the exact area under the curve given by this function on the interval 1 to 3. So let's do that, and we're going to do that using this limit. Now, how do we set it up? Well, it's kind of a pain to set up, but let's see. So a equals limit as n goes to infinity of the sum from I equals 1 to n of f of x sub I delta x. So now we need to figure out what f of x sub I is and delta x. Well, delta x we can find, where do I want to find delta x? I'm going to write it here, and then I'm going to erase it as we go through the computation. How do we find delta x? Well, take our interval 1 to 3. We're not dividing it into a number of pieces anymore. We're dividing it into a variable number of pieces. We're dividing it into n pieces. So we're still taking the interval 1 to 3, which has length 2. We're dividing it into n pieces. So that tells us the base of each rectangle is going to be 2 over n. Observation 1. Maybe I'll say equals in this case. Oh no, maybe I'll say it equals on the other side. Delta x equals, I don't need that anymore since I wrote it up there. Delta x equals the length of this interval divided into n pieces. Observation 1. Well, observation 2, well that gives us delta x. What about these x sub i's? Well, the I, first of all, is going to be counting us through our rectangle. It's going to be counting us through the points on the x-axis. Delta x is 2 over n. I'm going to take that delta x and put it in front. delta x is 2 over n. I'm just going to write that out front like this. Equals limit n to infinity, sum I equals 1 to n of 2 over n. What is f of x sub I? Well, f of x sub I, first of all, we're using the right endpoints. We're not using f of x sub I minus 1 here. So we're using the right endpoints. So what is our first endpoint we're choosing? It's not this one. The first endpoint we're choosing is that one. And how do we find that? Well, we start at 1 and we go over 2 over n. So it's 1 plus 2 over n. Okay, great. What's the next one? Maybe I should have drawn this interval a little bigger. Let's get 3 out of my way. I don't want 3 there. What is the next one? Well, so we started at 1, we moved over 2 over n. Well, here we start at 1 plus 2 over n, and we go over 2 over n. So it's 1 plus 2 over n plus 2 over n, also known as 1 plus 2 times 2 over n. Yeah, I definitely should have drawn this interval bigger. What is the next x value? Well, it's this plus another 2 over n. So it's 1 plus 2 times 2 over n plus another 2 over n. And so on. But you can see here the pattern that's forming. 1 plus 2 over n, 1 plus 2, 2 over n's, 1 plus 3, 2 over n's. 1 plus 2 over n here is 1 plus 1, 2 over n. So why don't I rewrite that like this? Started at 1 and we went over. Now, this I value, counting from 1 to n, is going to count us through these endpoints. And because of that, this counting, so 1, 2, 3, 4, and so on, in our with our notation, is just going to be I. But the rest of it will not be captured by the I. The rest of it is telling us how much we're moving. It's telling us where we started. So we start at 1, we go over 2 over n, we go over 2 over n, I times. And for simplicity, I'm going to write this I value in the numerator, because I times 2 over n is 2I over n. So to figure that out, remember the I counts us through the endpoints. Here we have the first endpoint, the second endpoint, the third endpoint. We move over 2 over n each time, and we start at 1. And this right here gives us our, well, it gives us the limit we need to compute. And in the approximations, I find finding the endpoints most complicated. In the exact limit, I also find finding the endpoints most complicated. So how can we do this computation? Well, it might not fit on this board. But for now, we still haven't taken a limit. We haven't taken the sum yet. But let's find f of I plus 2 over n. Jeez, I didn't say that. Let's find f of 1 plus 2I over n. So we first have 2 over n, and then we need to multiply by f of 1 plus 2I over n. Well, that's this quantity, with x replaced by 1 plus 2I over n. So all we did here is replace x with 1 plus 2I over n. Well, let's simplify that more. One plus 2I over n squared. Well, I'm going to, just put this thing first. 2I over n squared is 2 squared I squared over n squared, so 4I squared over n squared, plus 2 times this, so 4I over n, plus the second thing squared, So this quantity becomes, it's the a plus b all squared. So we get 4i squared over n squared plus 2 times that. So that's 4i over n plus the last thing squared is 1, because 1 squared is 1, so 1 squared, and then plus 3 will give us a 4 there. Now, how do we simplify this? Well, before simplifying, I'm going to erase up here first. I'm going to bring this to the top of the board. Well, I'm not going to bring it to the top of the board. I'm going to simplify the next step on the top of the board. So what does this equal? Well, I'm still not going to take the limit, and I'm still not going to take the sum, but I am going to distribute this 2 over n through. You could, if you want, pull out an 8. I'm not going to. Distribute 2 over n onto this, you get an 8i squared over n cubed. Distribute 2 over n onto that. You get 8i over n squared. Distribute 2 over n onto that. You get an 8 over n. And I'm going to throw parentheses on that because that's technically all in the sum. Now, how do we add, well, how do we take this sum? We're not going to take the limit yet, we're going to take the sum first. How do we do that? Well, I'm going to erase this, and I'm going to give you 3 equations. I have 2 of the 3 equations memorized. I do not have the third of the 3 memorized. If you had one of these on a test or a homework or something, I would tell you these equations. I would not expect you to memorize these. I don't know. When I was in grad school, the professors had the students memorize the equations. I thought that was completely unnecessary. Because I'd be teaching part of the class and I'd have to reference these because I can't memorize equations anymore. Recall these 3 equations. Everyone knows that. Recall these 3 equations. That was sarcasm on the first one when I said everybody knows that one. That's the one that I can't keep memorized. The second 2 I actually do have memorized. Well, the last one, I don't even want to. Let's talk about these a little. Let's talk about the last one first. The sum from I equals 1 to n of 1 is n. Why is that? Well, remember, this is counting out these terms and substituting I. So when I equals 1, what do you get here? 1. When I equals 2, what do you get here? 1. When you replace all i's with a 2, you still have a 1. When you replace all i's with 3, you still have a 1. And this keeps going until you let I equal n. You replace all i's with an n, and you still have a 1, because that's a 1. So you have... That's a pretty nice curly brace. So you have, what do you have? You're adding 1 together n times, so that's n. You add 1 together 4 times, 1 plus 1 plus 1 plus 1, you get 4. So this one equals n for a reason like that. What about the next, the other 2? Well, the other 2, to prove the other 2, you would use something called mathematical induction, which is an introduction to proof theorem, well, result, I should say. So we won't talk about proofs of these, but what does this actually say? What is this saying to add together? Well, let I equal 1, you get 1. Let I equal 2, you get 2. Let I equal 3, you get 3, and so on until n. You add the numbers 1 plus 2 plus 3 plus 4 plus 5 all the way up to n. It will always equal n times n plus 1 over 2. You know, you could check with like bowling pins. Add 1 through 4, you get 10. Let n equal 4, you get 4 times 5 over 2, which is 10. And what about the top one? Well, that's more complicated. But what do we add together? Let I equal 1, you get 1 squared, which is 1. Let I equal 2, you get 4. Let I equal 3, you get 9. Let I equal 4, you get 16. And all the way up till n squared. The sum of the first n squares is given by that equation, n times n plus 1 times 2n plus 1 all over 6. Now how can we use that to help us here? Well, we're going to use that to take the sum of I squared, the sum of I, and the sum of 1. So let's do that. We still have not taken a limit, but this observation will allow us to get rid of the sum. So what do we have here? Well, I'm going to first write a big parentheses. I'm going to next write 8 over n cubed, because this is going to allow us to get rid of I squared. So 8 over n cubed, just pull out, and we can replace the sum of I squared with that quantity. Oh, I'm not going to have room. So let's do this. We haven't taken a limit. We have 8 over n cubed. That's a 3. And we replace the sum of I squared with that first quantity. N times n plus 1 times 2n plus 1 all over 6. And we do that with these other quantities as well. So for the next one, we have 8 over n squared. And we replace the sum of I with n times n plus 1 over 2. And then the last one, we have 8 over n times 1. And we replace the sum of 1 with n. So all we did here was replace the sum of I squared, the sum of I, and the sum of 1. And notice in doing so, we were allowed to get rid of the sum because the sum has nothing to do with the n's. The sum only has to do with the i's, because the sum counts by i's. Now, how do we solve this limit? Well, let's see if my other marker is a little darker. Yes, rhymes just come out of me. Where are we? How do I want to do this? No, I don't want to do it like that. We now have the limit as n goes to infinity of a bunch of things, and we know how to compute that because we just have n's. We have a what's it called? A polynomial on top and a polynomial on the bottom. So I'm just going to write these as one fraction each. Over here, the 8 and the 2, notice they become a 4. Over here, I also, maybe I should have said that also. The 8 and the 6 make a 4 and a 3. Oh, jeez. 8 and the 6 make a 4 and a 3. Now, how do we do these limits? Well, this last one, the limit is 8. How about the first one? Well, for these examples, you can use an observation I mentioned last week during our workshop. Last week during our workshop, I mentioned if you have the same degree on top as on the bottom, the limit as n goes to infinity would be the ratio of the leading coefficients. So in this case, what is the ratio, or what is the coefficient of n? Well, what is the coefficient of n cubed? 4 times 2, so 8. What is the coefficient on n cubed here? 3. Over here in the next piece, what is the coefficient of n squared? It's 4 on top. What is the coefficient on n squared on the bottom? 1, so 4 over 1 is 4. The last one is 8, that doesn't change, and then goes to infinity. And then you add these together, what do you get? You get 8 thirds plus 12. 8 thirds is 2 2/3. So you get 14 2/3. If you wanted to write that as one fraction, what would it be? 44 thirds. So this computation, I mean, it's not an easy computation. So I have in the past asked one of these on the final exam. So this is week 4. Our exam is week 6. That might not be necessarily enough time for this entire computation to be digested. So you can keep that in mind. But I have asked it on a final exam. But to set it up, the first thing we did was look at the x values in order to substitute for f of x sub I. Then we figured out f of x sub I, did some simplification until we got to something that looked like this, which allowed us to replace all sums of I squared, sum of I, sum of 1, with something in terms of n. And from here, we set that up. We just reorganized it a little to get to this step. And then down here, I'll say week, this equals sign, week 3 workshop observation. From that observation, we could look at the ratio of the coefficients on each piece. I mean, if you didn't use that observation, how would you do it? Well, you'd multiply all these things out on top, divide everything here by n cubed, divide everything here by n squared, and then take the limit as n goes to infinity. But this computation is very, very important in math. Now, why is it important? Well, at the beginning of this video, I said a goal in calculus is to find the exact area under a curve. Well, here we go. We found the exact area under that curve. And we could do this for any curve on which there any curve which is defined on a relevant interval. Now, do I want to give it away now? This is week 4. During week after exam 2, so I believe exam 2 is week 11. So during week either 12, the end of week 12 or week 13, we will see that a very important theorem in math will tell us we can compute this area in a different way, which takes fewer steps than however many steps this took. But without a future theorem in this course, if you wanted the exact area, you would have to go through a limit computation just like this one. So there is one of these on the worksheet. Try working through it and see what you get. I will go over it during the workshop. I'll probably go over it last during the workshop because it might take a while. But try working through it, see what you get. I personally find, in this case, turning the points on the interval into 1 plus 2i over n, I find that to be the most difficult part of these. Because after that, there is a lot of writing, but if you take it slowly, carefully, and make sure you're keeping your fractions organized, it does work out in a very similar way to this one. So see how that goes.